The sun, our sun. This is the sun today. This is taken from an observatory in space, the Solar Dynamics Observatory. It's probably not what you're used to seeing or thinking about the sun, because it's not the sun as we normally see it. This is an image of the sun in the ultraviolet. And I'm going to talk to you a little bit about some of the observations that I've been involved with. I've worked in solar space observations for about 3 decades now. I worked on Skylab, Solar Maximum mission. I took my 2 now beautiful daughters. They were beautiful then, but they're even more beautiful now. With me to Goddard Space Flight Center with my husband. And I've worked on SOHO, and more recently on Hinode and the Solar Dynamics Observatory. The sun, our sun. It's a middle-aged star. Middle-aged, a little bit like me, although I'm heading towards the older age now. It's our source of energy. It's huge. The Earth would be about the size of that sunspot there. The surface temperature is around about 6,000 degrees, and this may be an image that you're more familiar with. The energy in the sun is produced in the core of the sun by fusion, turning hydrogen to helium. Then propagates through this radiation zone, and just beneath the surface there's a convective layer. It's constantly moving. The energy is transported out and then radiated out as light and heat. Here's one of my favorite astronomers, Galileo. Not just because he lives in Italy, but it does help. Galileo had his own telescope, one of the first people to use a telescope to look at astronomical objects. And he studied the planets and the moon, but he also studied the sun, projected an image. And these are his drawings of the sun. And he associated these sunspots with the sun and saw that the sun rotates. So the sun takes about 25 days to rotate around once at the equator. Galileo got into a lot of trouble for his science beliefs. The fact that the Earth goes around the sun. And also because of these sunspots, because all astronomical objects were supposed to be perfect. They weren't supposed to have blemishes and black spots on them. He was kept under house arrest. And this is a view from his window in Arcetri. It's now part of the observatory in Arcetri. I visited. Don't feel too sorry for him. It was a beautiful village, it was a beautiful view, and the wine cellar was full. So these sunspots are important because they tell us how active the sun is. When the sun is quiet, there's very few sunspots. And when the sun has many sunspots, the sun is very active and can produce storms, which result in aurora. So here's an image of the sun showing the rotation again. We can observe the sunspots here on the ground in projection. Never look at the sun, health warning, never look at the sun, will make you go blind. You can project it, or you could look at it with an H-alpha telescope with a special filter. This is a photo from my friend Ninian, who runs a site called Astronomy Know-How, and this was, as you can see, just taken a few days ago, earlier this week. So in fact, at the moment, we do have, and this is up close, we do have a few sunspots on the sun. We take these telescopes to Glastonbury, to the music festivals, and people are amazed that they can actually view. We also have nighttime telescopes there as well, and if the weather's good enough, you can see the moon at nighttime and the sun in the daytime, all within 24 hours. So the sunspots, as I said, they're not constant. They come and go. And this is the year along the bottom here, and the number of sunspots that you see on the sun. And you can see it has a cycle. Sometimes there's very few, none at all, and sometimes there's a lot. And this cycle is approximately 11 years. And this is the cycle of solar activity. At the moment, we're at a time when the sun is quite active. You saw the sunspots just then. It's not quite as active as we think it should be, but it is quite active. Another of my favorite scientists, mathematicians, astronomers, not least because he worked in Cambridge at Trinity College. And sometimes when I walk along the backs of the Cambridge colleges, I imagine that I'm walking in his footsteps. And I'm hoping that just a little bit of his intelligence might rub off. I keep hoping. Of course, he's renowned for his work on gravity, but he was also extremely interested in colors, in light, in the nature of colors. And he's getting a chink of light here, passing it through a prism. The reason he was interested in light was because he was also interested in astronomy. And the colors in the refracting telescopes, which used lenses, used to mess up the images. They were an aberration. And he wanted to understand where those colors came from. But he actually built his own telescope, which used mirrors instead of lenses, a reflecting telescope. He studied the light, and he realized that white light was made up of the component colors, and that if you took one of the blues or the reds and put it back through the prism, it stayed blue or it stayed red. He wrote a treatise on optics, and I can't see very well, but I think we've got a few ladies in the audience. This is a translation of his thesis for the use of ladies. I haven't actually read it. I should read it. I should find it and read it. I might learn something. So we're going to step aside a little bit and to do some demonstrations. We're going to look at the spectrum. We're going to look at continuous spectrum. If we go beyond the visible, which is all our eyes can respond to, we go into the ultraviolet, X-rays, cosmic rays, gamma rays in one direction. If we go beyond the red in the other direction, we go to the infrared, the radio in the other direction. So I think with my handy assistant, Andy, we're going to try and do a few little demonstrations. This is a continuous spectrum, in a continuous emission in the visible. One can also get an emission spectrum if you put a particular gas in the way of the spectrometer, and we could get an absorption spectrum if we shine the light through a gas. So, what we have here is not a prism to get the light, but it's actually a diffraction grating. You've got a very simple diffraction grating everybody has in their house. It's just a CD-ROM. And you can see with a CD-ROM, as the lights go down, you can see the colors formed by the diffraction grating as light is broken up into its colors. So here you've got a slit, we've got a diffraction grating in there, and we can see the colors of the light being broken up there. Thank you, Andy. Now we're going to try it with something different. This is something we made earlier. This is with a lamp. And we don't see a continuous spectrum anymore, but we can see lines at particular wavelengths. We're going to try something really spectacular. So we're going to light this, stand back. Where are the fire exits? You've told them where the fire exits are, have you? We've got some sodium here. Ooh, let's set fire to it. There we go. And we should, hopefully, see some faint lines somewhere if we're lucky, off to the side somewhere. Here. You saw them? I just saw it a minute ago. Here. Some lines, some spectral lines from the sodium gas. They're yellow. They're in the yellow wavelength range. Thank you, Andy. We put the fire out. Can we show some of the ultraviolet at the same time? Yes. We can't see ultraviolet light, but we can detect it. Certain chemicals respond to it, certain things respond to it, and we can use detectors. So we've got an ultraviolet lamp. I think we're going to need, you're going to hold the lamp?
Yeah, I'll hold the lamp. Yeah.
We're going to need to turn the lights down a little bit, I think. So what we've got here, we couldn't see previously, but maybe we can see now. Do you want to turn it around? What does it say? Hello. Okay. Hello. We're going to do Andy's teeth in a minute.
Oh, yeah.
Look, go on, show them all. Over here. Yeah, here, clean them specially. We've got, is that coming up? We've got some detergent in there. So sometimes maybe if you've got your laundry done well enough, it shines up white. So probably your shirt cuffs would probably, oh yes, Andy's cleaned his shirt. Well done. So what do we have? We have the continuous spectrum from a prism or from a grating. But if we have a certain gas, it can give us these emission lines. If we shine the light through a gas, it can absorb at certain wavelengths. And these are very important. This is how we know about almost all the astronomical objects that we can see from the radiation. We can't go out there and sample them all, but we can see the radiation that comes from them. And we can tell what they're made of. This is the color scheme for hydrogen, for helium, for nitrogen, for neon, argon, and mercury, for example. I've likened it to the bar chart in Tesco's checkout. Basically, it tells us what we're buying if we don't already know. These spectra can also tell us many things. They can tell us even about the temperature of the gas, about the density of the gas. But we don't just need to use the spectra in the visible. We can use the spectra in the ultraviolet and the X-rays as well. So this is an image of the sun taken in helium emission. So we take a small line where the helium is formed, and this is what the sun looks like in the helium emission. This is actually from a Skylab, and you can see a huge eruption on the side of the sun here. So helium was actually first discovered on the sun. Helium comes from the Greek word helios, which means sun. Incidentally, my name, Helen, also comes from the Greek word helios, which also means sun. So I've got a feeling it was my destiny to study the sun. Who's seen a total eclipse of the sun? I know my oldest daughter hasn't yet, but we will do one day. Was it impressive? Yeah? Did anybody see it here in the UK? 1999? Well, I know you did. You were with me. Who else did? Quite a few people. In Alderney? At the National Astronomy meeting, or maybe in Cornwall? I think in Cornwall they saw it, the total. Unfortunately, the weather wasn't so good in many parts, but we did see it in a couple of places. It is awesome. And it's awesome because it's the only time, really, that we see this atmosphere of the sun. It's called the corona, a crown of light around the sun. The moon is blocking out the main disk of the sun. And the main disk of the sun is about 1 million times brighter than the light that's given out by this atmosphere. So we normally can't detect it. We can simulate it with something called a coronagraph, which is an instrument that blocks out the main disk of the sun. So during a total eclipse, we see this corona, this outer atmosphere. And it's this that really fascinates me and that I've been working on. You can see many structures here. But I'll say that an eclipse is, did anybody find it eerie? Did anybody, yeah? It's quite almost scary when it happens. Even for me, and I know exactly what's happening. I know exactly I'm a scientist, I study it. I know exactly what's happening. But it's quite eerie because in the middle of the daytime, the sun starts to go out and it gets cold and it gets quiet and the animals respond. Where we were in Alderney, we were up near a harbour and the lights on the boats came on in the daytime, nighttime. It's very eerie. I'm not at all surprised that it was a very frightening experience for ancient people. Now, something mysterious about that corona. When you took a spectrum of the corona, when they had an eclipse and they did some scientific observations and they took a spectrum, they saw some bright emission lines. These are like the bright lines we saw earlier. There was one in the green, yellow, red, bright lines. But they couldn't place them. They didn't match. The fingerprints didn't match any of the elements that they knew about. They couldn't match them up. They did a lot of work to try and find out what they were. Now, scientists sometimes have good ideas. Sometimes the ideas are not quite so good. Anyway, they decided that they would invent a new element called coronium. They had had such a lot of success with helium. You know, we're on a roll now. Let's go for coronium as well. The problem was, as you will know, the elements have to fit into the periodic table. And there really wasn't a space for coronium. So that was one of the scientific ideas which perhaps wasn't one of their best. It took a lot of detailed laboratory measurements and work and investigations to realize that actually this coronium was just iron, just normal iron that you find, but very, very hot. So iron normally has 26 electrons around the atom, inside the atom, around the nucleus. It melts at about 1,500 degrees, becomes a gas at about 2,500 degrees. The sun's surface is 6,000 degrees. Everything is a gas. But actually, that corona is a whopping 1,000,000 degrees. It's 1,000,000 degrees. And as the temperature rises, more and more electrons get stripped off the atom. So at 1,000,000 degrees, 13 of the electrons that normally orbit around the nucleus are stripped off iron. We call this an iron of iron. We have different ways of notating it. Iron plus 13 or iron 14. So the corona, the outer atmosphere of the sun, is very hot. And because it's very hot, it emits very strongly in X-rays and ultraviolet. And this is an image in X-rays from a satellite called Yoko, a Japanese satellite. And you can see it's rather strange. All of this gas that we see here, we call it a plasma because it's ionized. All of this plasma is 1,000,000 degrees or more. You can see at the top here a dark patch. And this is a patch where the corona has gone. We call it a coronal hole. We're very inventive here. It's a hole in the corona. The corona has gone. And these are regions where the very active regions and the sunspots are underneath. Now, the sun and the shape of this is controlled by a magnetic field. Because the gas is charged, it traces out the magnetic field. This is a comparison of an X-ray image on this side and our normal sunspot image on the other side. It's rotating very fast. I haven't managed to slow it up. But you can see, more or less, that the sunspots are where those very active X-ray regions are. The X-ray emission from the sun doesn't stay constant. It has a cycle, like the solar cycle. So it has an 11-year cycle. So when the sun is very quiet, there's very little X-ray emission. It's dark here. But when the sun gets more active, there's lots more. So that X-ray emission changes with the solar cycle. So now I'm going to tell you a little bit about SOHO, which is a satellite that I've worked on and has produced some spectacular results. It's given us a completely new perspective on the sun. It was launched quite a while ago now, in 1995. It's a very sophisticated satellite. It has 12 different instruments, some of which are used to study the inside of the sun. I'm not going to talk too much about that. Some are used to study the solar atmosphere, and some are used to study the solar wind. Now that's where the corona has drifted off into space. Okay. The shape of this here is a little bit like the dipole of the Earth. So if you can imagine, the magnetic fields come around here, and at the top here they're open. So here the gas is trapped, and here the plasma, the ionized plasma, has escaped. Where is SOHO? SOHO's in a very strange orbit. It's still operating. We did lose it for a little while, I must admit, which was a bit of a scary moment, but we found it again. It's between the Earth and the sun. But it's 100th of the way between the Earth and the sun. So if I'm the Earth and somebody up the back there is the sun, it's very close to me. But it's actually orbiting the sun with the Earth. So it sees the sun continuously. So it's in a very strange orbit. Most satellites would go around the Earth. And this is an image of the sun in ultraviolet from SOHO. Now the sun is green. Green sun. Okay? That's because we can't see ultraviolet, so we can make it any color we like. And we do like to make things colorful. They're not too keen on the pink, although we have persuaded them to use pink. But purple, blue, green. And we use different wavelengths of different colors. So this is actually responding. This is at an ultraviolet wavelength, and it's responding to the plasma, the gas, at 1,000,000 degrees. And here you can see some active regions. You can see how much it's changing. It's rotating. It says 25 days to rotate. You can see things growing and changing and moving. You can see down the bottom there is another hole in the corona. It's a dark patch, and up the top here, another coronal hole where the magnetic field is open. This is a comparison between solar minimum and solar maximum. You can see during solar minimum there's very little ultraviolet emission, whereas in solar maximum we've got lots of activity and lots of strong ultraviolet emission. And this is an instrument on SOHO which measures the magnetic field on the surface of the sun. So positive and negative polarities coming and going. And this is constantly moving and changing because of the convection just beneath the surface and magnetic fields erupting up through the surface. So if we did a little model of this, and this is just a sketchy model of what the magnetic field looked like for this particular region, we can see some of the field lines are open and then some of them are closed. And this is actually today's sun. What they've done with the Solar Dynamics Observatory is to measure the magnetic field on the surface of the sun and then to extrapolate what the magnetic field probably looks like higher up in the solar atmosphere. So again, you can see some magnetic fields wide open and some closed, but constantly changing. Now this is a fly-through of the magnetic field, artist's impression. Here's the magnetic carpet on the surface of the sun, and here we are flying through it, and it's constantly moving around. In fact, it changes every 2 days. It's like having a carpet in the lounge, which is going to change every 2 days, the pattern on the surface of the sun. The sunspots are regions where the magnetic field comes out from beneath the surface and then goes back. Here's the sunspot region, and here's the ultraviolet emission, shown there. Very hot loops of gas. Another artist's impression. Here's an ultraviolet, this is the edge of the sun. Here's an ultraviolet loop, an active region, and it's as if there's a little bar magnet there lying on the end. And the magnetic field has popped out and gone back in again. Right, now we're going to do a little demo of the magnetic field. And this is very interesting because it's actually reproducing what Faraday did to demonstrate the magnetic field. This is one we produced earlier. No, I'm not going to show you the one we produced earlier, just in case it doesn't work when we put it in the oven. So what Andy's doing is shaking some iron filings. There's a magnet underneath there, just a bar magnet. It's just a normal north-south bar magnet. He's shaking some iron filings to get the pattern of the magnetic field on there. He's going to give it a little tap in a minute, because I've seen this done before, just to get the pattern of the iron filings. Now, very cleverly, lifting it very carefully so he doesn't drop the magnetic iron filings everywhere, and with my help so that I can slide it on. This is wax paper, isn't it? Yeah. We're going to put it, oh, it's very hot now. It's melted immediately. Okay. We're putting it on a hot panel, I guess, what would we call that? To melt the iron filings onto the wax. So this isn't the exact same hot plate that Faraday used, but it's the way he used to demonstrate. And you're going to slide it off? You all right? Okay. Woo! Well done, Andy. Take it around and show everyone. You want to walk it over that side as well? My beautiful assistant. Okay. So earlier today, we were very honored to actually see some of Faraday's original iron filing pictures. They're very delicate, so they're not on public display. Thank you. But what we do have here, which you can have a look at afterwards, is some plates that he made. On the back says what the magnetic field looked like. So we can come and have a look at those afterwards if you'd like to. So those are Faraday's original plates. So magnetic field is very important on the sun. And the gas traces it out, so we can see it. Just as the iron filings there trace out the magnetic field, so the hot gas, because it's ionized, traces out the magnetic field. Right, so what about these sunspots? Let's think a bit more. I said the sun rotated with 25 days in the center, but it actually rotates a little slower at the poles. It only takes about 30 days at the poles. And it also rotates inside. We know this from helioseismology, waves going through the sun that have been studied. The magnetic field comes from the inside of the sun, but as it does, it's formed inside the sun, in the layer between the radiative zone, just beneath the convective zone. As it does, and the sun rotates, it gets twisted up. Because the equator is rotating faster than the poles. It gets twisted up, and eventually it pops through as twisted magnetic fields. It pops through the surface in these active regions where the sunspots are. And now I'm going to tell you a little bit about solar flares. They are huge explosions of energy, massive. Temperatures can reach 20 million degrees. Here's a flare taking place. That's a blow-up of this little area. It's burnt the detector out. That's why it's got a streak there. The detector on SOHO is burnt out. This is in the ultraviolet. Flares are classified by the amount of X-ray radiation that comes up from them. And this is the X-ray emission. And here, ABC MX is the classification for the flares. The X-ray is quite quiet, then suddenly shoots up. If it shoots, M flares are quite common, C flares are quite common. X flares are quite rare. But if it shoots up really high, it's a really big X-class flare. We, solar researchers, like X-class flares. She really likes any sort of flare. However, they do have consequences. Carrington and Hodgkin are credited with seeing one of the first solar flares in 1859. And this is a drawing they made in the visible. They saw it in the visible. This is an X-class flare seen by Solar Dynamics Observatory. We have seen some X-class flares. And again, the detector here is well burnt out. We get so many counts. It goes up by orders of magnitude. And here's a flare in the ultraviolet that's just gone off, and these big loops formed. Now, this is the sort of model, the standard model we have for a flare, with the magnetic field changing here, erupting, this whole system erupting up, going off, bang, and then these loops forming underneath. Magnetic energy is transferred into other forms of energy, into heat, and into particle acceleration. You can see those beautiful loops forming. This is a model, theoretical model, just an idea of a magnetic field breaking through the surface with the overlying magnetic field. And again, that is disrupting the magnetic field above it and heating it. The red is getting hot. This can cause huge eruptions. This is the helium emission again, but you can see this huge eruption on the side, shooting out into space. This is an eruption that was seen by the Solar Dynamics Observatory. Just look how big that is. Where's the Earth? Oh, it was about that big there, the Earth. This eruption was huge off the side of the sun, in helium, seen in helium emission there again. And here's a little movie at different temperatures. There's a little region here blown up at different temperatures there, 50,000 degrees, 600,000, and hotter. And you can see an eruption taking place and how it forms. So we can dissect the temperature structure of some of these events by looking at different wavelengths, by looking at different spectral lines. There's another really impressive eruption coming off the sun there. Now, I was going to do a little demo of the solar flares. Have I got there yet? Oh, yes, I have. I've passed that as well. Right, I need, a couple of volunteers who, is Andy going to volunteer again? Come on, Andy, you're looking very smart. Okay, give it a shake. I need somebody else to come up here and stick a pin in this balloon. Do you want to stick a pin in this balloon? Come on. Stand back when you do it. Okay, have you got it carefully? Right, you're going to go and stick a pin in that balloon? I wonder what's going to happen. Hold it tight. That's it. Give it a shake, Andy. Right. Oh, is it going to go? Oh, I might have to help you. I'll have to help you. Stand back a little bit. That's it, stand back. Give it a shake, Andy. Okay. Woo! That was a bit scary, wasn't it? Hey? Yeah, wow, that was a solar flare going off. Hey? Thank you. Yeah. So what's happening is that normally the magnetic field is holding that solar flare down. It's holding it together. But then what happens, I've got another one here, then what happens, I'll pop it afterwards, is that basically something comes and disrupts that magnetic field, just as the pin, I'm quite glittery myself here now, just as the pin broke the skin of the balloon, which is holding that in. So the magnetic field gets disrupted, and the flare suddenly explodes. So the magnetic field can pop up from underneath, and one of the things we try to understand is what does disrupt that solar flare? What makes an active region flare? When it does, it can have spectacular effects. This is a massive ejection of material. The sun is here. This is the sun. This material has shot out into space. We call this a coronal mass ejection. Huge speeds, 200 kilometers per second. Here's an image from SOHO. I'll run it again in a minute. The sun is blocked out here, and you can see material shooting out into space. You can also see, if you look carefully, you can see two little dots going by, and they're comets going round. SOHO's seen a huge number of comets. Here's another one. The sun's actually a montage here. It's actually blocked out, but they put an image of the sun in here at the same time. And you can see an eruption here shooting out into space. Here's another one with the sun in the center here. And you can see material. The sun is smaller here, a bigger field of view. In fact, you can see the stars in the background, and you can see material shooting out into space. This one, whoo, what happened there? Anybody? Yeah, you're reading it, aren't you? Cheating. Yeah, I know. It's coming straight for us. What's happened there is that CME, instead of going off to the side, has come and hit SOHO. And that snow is particles that have hit the detectors of SOHO. And if it hits SOHO, it's going to hit us. Because as I said, SOHO is 100th of the way between the sun and us. So that CME is heading straight for us. Now, it's heading for us. Here's the sun shooting out CME. Here's us. We're protected by our own magnetic field. So we have some protection from the solar wind that flows off the sun and from these explosions which come towards us. But some seep in, some break through and restructure the magnetic field on the Earth, causing beautiful effects like the aurora, northern lights, southern lights. Who's seen an aurora? Lucky people, I'm going to see one day. Okay, and here's a movie. This is the best I can do for the moment. And you get the beautiful colors in the sky caused by the atoms in the atmosphere, oxygen, nitrogen, others, getting excited by particles that are formed because of the solar storms and producing these wonderful effects. But it's not all good news, I'm afraid, because not only can we have beautiful effects like aurora, but unfortunately these solar storms can also affect satellites. They can affect humans if they're walking in space. They can even affect the flights if they're going over the poles. They can knock out, in extreme cases, they can knock out electricity grids. And it is predicted that if we had a flare as big as the one Carrington saw, a big X-class flare, it could be problematic for us, even in this country. And because we now live in an age which is so dependent on technology, if our technology breaks down, if our iPhone isn't working, if the electricity goes and we can't get any money out of the bank or get the petrol stations to work or do anything, we've got problems. But it's also, of course, extremely expensive if a satellite is knocked out. And if business can't carry on. So one of the things we try to do is try to be able to understand what causes these coronal mass ejections, what causes these flares, and can we predict them? Now, this is some work I did, quite a long time ago now, with SOHO. And we were studying something called solar tornadoes. And I was really pleased because this got the front page of the Daily Mail, which, is a scientist's dream. Unfortunately, when you look at the small print, scientists fear deadly tornadoes around the sun will cause havoc with our satellites and wreck communication systems. I mean, we were worried. Even coverage of the World Cup could be at risk. What more can I say? I'm going to tell you a little bit about a project I've been working on recently, which is a joint Japanese-NASA UK project. We have the lead team in Mullard Space Science Laboratories at University College London. And it's a satellite to look at the structure of the solar atmosphere, at the surface and the atmosphere. And we're working with this observatory to try and understand features on the sun, connections between the magnetic field as it changes on the surface of the sun, and what effect that has on the upper atmosphere. It was launched in 2006. One of the interesting features with a spectrometer, I don't know whether people have heard about things called redshifts. If you hear a train go by, you'll hear the whistle go, yeah, like that. That's a Doppler shift. Because the train is moving, the frequency changes. And it's the same with spectral lines. The spectral line shifts slightly, and we can tell the motion of the plasma or the gas. And here, blue is moving towards us, and red is moving away from us. And one of the interesting things about the spectrometer that I've been working on is that we've seen these flows in these. This is an active region, and we've seen these flows in the active regions. We've seen blue shifts where gas is escaping from the sun, possibly. It's certainly moving up, and we've seen red shifts where the plasma is falling down. And we're working with theoreticians to model this, to try and understand what's happening. This is plasma at 1 million degrees. Just a very small amount about what I do, or my speciality. I study these spectra. This is a spectra from that instrument, from 17 nanometers up to 28 nanometers. We work in angstroms, but in nanometers, it's 17 to 28. And there's lots of spectral lines there from different ions. And from that, we can understand the temperature, the density, what elements are there. But in order to do that, we have to do calculations to simulate what we might be seeing. We have to study each of the atoms. And we've put together this huge atomic database, which is used to analyze these spectra. And we called it something nice. Called it Chianti because then we thought people would use it, and it's worked. It doesn't actually stand for anything. We tried to make something up, and it just made us feel good. And as you can see, we enjoy meeting in Florence as well. This is at our Cetri Observatory. One of the collaborators is from our Cetri on the balcony there. So we've got a team together. So this is basically my bread and butter work, and now this is universally used by all the solar people to analyze their data. Stretches from the ultraviolet to the X-rays and beyond. So I think I'm winding up now. I started just a fraction late, so I just want to say a few things I've talked about the effect of the sun, solar storms, space weather. I wanted to just address briefly whether or not solar activity can affect the climate. And you can see here these penguins are looking pretty worried. The icebergs are melting. There is a lot of evidence that the ice is melting in the Arctic and the Antarctic. If we look at the sunspots over 400 years, so this is from 1600 to 2000, we can see it varied a lot. I said there was a cycle of sunspots, an 11-year cycle, but actually there were periods when there were very few sunspots. This is called the Maunder minimum, and it wasn't because they couldn't measure them. They were measuring them. They just couldn't see them. And this corresponds to a period called the Little Ice Age in the northern hemisphere, where the Thames froze over and everybody was skating around and enjoying themselves and having a lot of fun. So there definitely is a correlation between solar activity and climate. But it's complicated. The actual visible emission doesn't change very much. But as I showed you, the ultraviolet and the X-ray emission changes quite dramatically between solar max and solar min. And that's something we don't fully understand, the effect that has on the Earth's atmosphere. We don't fully understand that yet. And it's something actually we've got a project going in my group to define more carefully what the actual solar emission is in the X-rays and the ultraviolet. So here's the sunspot cycle again, done slightly differently. These are the number of sunspots going up to 2010. And where they appear on the sun, this is called a butterfly diagram. They appear at certain latitudes and then sort of move down to do with that rotation that I showed you earlier on. So the question is the sun affecting, is it a parameter? It is a parameter, but how much might it be affecting climate change? So here I've plotted the temperature change over a period of time from 1880 to 2010, I think that is. And the solar activity. Now, solar activity can be measured by proxies. It can be measured in different ways, and this is averaged over 11 years. And you can see there is a sort of correlation between the temperature and the solar activity. But look what's happened in the last 30 years. The solar activity is not increasing. It's not shooting up. If anything, it's going down. So the solar activity has remained constant or actually gone down a little bit, and the temperature has shot up. So there's very little doubt by the majority of scientists that the changes that we are seeing in climate are due to man-made effects, are not a consequence of solar activity. This is the sunspot cycle right up to recently, 2010, 11, 12, June 2012, and you can see the solar cycle, this cycle is not as big as the last one. In fact, it's even smaller, and we're rather upset about it because we really did want to see lots of beautiful flares. But it's actually quite a low one. So if anything, some people think we might be heading for a little bit of a solar lull or a minimum, which could, of course, be good news because it could cause the climate to cool a little bit. But unfortunately, it's not going to solve our problems, not for long. Now, I'm finishing up, and I just wanted to mention a website that we've put together. And Matt's somewhere here. Oh, he's up there. Yeah, Matt's been working on me with this. He's been doing some of the technical stuff. And it's about the sun. So it's called SunTrack. It's aimed primarily at schools, but actually it's accessible to anybody. It's got movies, images. Many of the movies and images that I've shown you here today are in the gallery. You can find them. It's got information about how to view the sun safely. In particular, it's a good opportunity for schools because it's daytime astronomy. It's got information about all the satellites that I've mentioned, SOHO, even Skylab, and also the most recent ones. I haven't talked about Stereo, but that's another satellite, Hinode. And it's got some classroom resources, some projects for classrooms. And I've got some little cards here if anybody wants to get the website. So that's the end. Thank you very much for listening.
You mentioned, the sort of potential for flares to sort of wreck the electronics communication systems on the world. Is there any way that one can sort of predict with any degree of accuracy when that might happen so that we can mitigate against it, or is that just asking far too much of modern science?
No, in fact, when a solar flare goes off, explodes, as we had there's two things. There's very energetic particles that shoot out. They are traveling very fast, so they reach us very quickly. And it's a little difficult to do very much about those. But the coronal mass ejections take about 3 days to reach us. So actually, we have, in the UK now, we have space weather warning. I think the Met Office is also involved in this, but the British Antarctic Survey is involved. So ways in which we might be able to predict or tell a number of hours, a number of days, in advance that there is a storm heading towards us, which could be problematic. So then it's possible to put expensive satellites into a safe mode so that you can ride out the storm, basically. So that work is going on. It's complicated, and it includes a lot of modeling that needs to be done as well. And the other thing we're doing from the solar end is to try and understand what causes these flares. We can tell. We have something called an S shape. I know this is a bit basic, an S shape. And what's happening is an S shape in X-rays, it's called a sigmoid, but the active region is getting very complicated. It's getting very twisted up. It gets very, very twisted up, and then eventually it will ping back to a lower energy state. So we can tell by the nature of the active region and how complicated it's getting, we can give a certain probability that a large flare or small flares. Some of these active regions are small flares all the time. They're not a problem, really. But you can give a probability of whether or not a large flare will happen. And we're trying to understand, from the scientific point of view, what causes that? What's the trigger? One of the things we worked on is what's the trigger? It can be in that state for a while, but what suddenly triggers it? And we think, at least some of the work that I've been doing, I think what happens is that a magnetic field erupts from beneath the surface and disrupts the whole structure. So it can erupt in one place and it doesn't matter, but it erupts in a critical point, then it can disrupt the whole structure.
Right.
Sorry, this sounds a rather flippant question, But how did you manage to measure 5 million plus degrees centigrade from here? I mean, I'm used to using fairly high temperatures myself, but that amount is out of this world. How did you do it?
Okay, we do it because when the temperature gets very hot, the atoms are not in their neutral state. So, for example, iron, which normally has these 26 electrons, they bump into each other. These electrons get knocked off. The spectrum changes. It doesn't stay as it is. So as I didn't say that, as it gets ionized, the spectrum changes because it's slightly different. The atom is no longer quite the same structure. And it goes on and on and on. So you can take 1 electron, 2 electrons, 3, up to 5 millions. You've probably got 14, 15 electrons stripped off. And it has a very characteristic spectrum, in particular in the ultraviolet, and we see those spectral lines, and we know that that gas is then that temperature.
Yeah?
Hi.
Hold it close.
Hi.
Yes.
I'm following on from the first question, which, if you're distributing communications, so whether or not it's television or news or films or whatnot, satellite versus cable underground, so cable television versus IPTV versus telco versus satellite. Presumably there's a difference between whether or not something's at satellite level versus underground, or how far
Absolutely,
underground it is.
Yeah, the underground it's the ones that are up in the atmosphere that could be affected, and it depends, what height they are as well as to how they're affected. So you mean the cables in the ground?
Yeah, so if we're trying to distribute news, for example, then if we have issues, then satellite technology is more likely to go offline.
Yeah.
And cable technology and telco IPTV technology, for example, is likely to remain.
Back to the cables.
Okay.
Yeah.
Thank you.
That's correct, yes.
Although the 1859 explosion did affect the telegraph system quite seriously.
Yes, you can get currents induced in the telegraphs as
Catherine,
well, that's right.
Yeah, I think. And then if you could pass it behind when you ask your question.
If you were traveling with the coronal mass ejection at the same speed as it, would it still seem the same temperature, or would it be much cooler?
Well, it'd be quite a ride, wouldn't it?
Well, it'd take a bit of acceleration to get there.
Would it be cooler as it goes out, you mean?
Is it very coherent? Is it all sort of all in one direction, or is it going in all directions, bouncing around like an ordinary gas?
It's going out like that. Is that what you mean? Do you mean?
Yeah, but I mean, for a particular bit of it,
Yeah.
are they all going in fairly straight lines, or is it bouncing around like a gas in this room?
Well, there will be motions in the gas, as there is motions in the gas in this room, and there are also shock waves maybe going through it as well. So they may be going out, and it will be going out in several directions. So the temperature, it's a very interesting question. It's a question, again, that we're trying to address. In a gas, we would normally have Maxwellian distribution of electrons or of ions or whatever, but actually, if it's skewed, it gets to be non-Maxwellian, and then it's quite difficult to actually define what temperature is. So I think in the answer to your question is the temperature is a little bit more difficult to define and to measure because the gas is not behaving in quite the same way. Does that make sense?
Okay.
Good.
I just want to ask, what causes the 11-year cycle of it being less solar activity, and then after 11 years?
Well, what causes the cycle is the magnetic field coming up, getting twisted up. In that little diagram I showed you, and then coming up, and then the magnetic reconnects. We get magnetic reconnection above the surface, and it dissipates, and then it starts all over again. And the north and the south pole of the sun swap over, and then they go back again. Now, you've asked a question that I don't think really people yet know the answer to. Maybe you can have a go at it. Why is it 11 years? Why does it happen like that? Is it the same in other stars? We've got some idea of how this dynamo works, but there's still a lot of detail there that's not really understood. So I can't answer the question as to why it's 11 years.
Okay, please.
One of your first points was that the sun is a middle-aged star. How much do you think the sun will be active before imploding on itself?
Well, it's going to say it's middle-aged. It's about 4.5 billion years. It's going to live for another 4.5 billion years. But before then, it's going to have burnt up all the hydrogen in the core, and it's going to start to grow into a red giant. So it's going to get bigger, okay? At that stage, we're looking for somewhere else to live, I think, basically. And then eventually that outer envelope will blow off, and it will just leave a small core.
Thank you. Yeah, my question was half asked, actually, and answered.
Okay.
But does that mean the 11-year cycle of the sunspots, that's effectively a measurement of the elasticity of the magnetic field?
You mean how far it stretches round?
Yes, because it's
Yeah.
if the sunspots are caused by the difference in rotational speed, but the rotational speed doesn't change, then it's effectively just resetting itself every 11 years, obviously.
Yeah, you could think of it in that way. Possibly, yeah.
Thank you. You mentioned the photosphere, 6,000.
Yeah.
And then you've got the atmosphere at 1 million. Why such a huge disparity, and why?
Okay, now I should have explained that a little bit more. Yes, it's counterintuitive. You know, you've got a bonfire there, you move further away, and it's hotter. Doesn't make any sense, which is why it took so long to realize. Now, one of the things we've been working on is trying to understand what is heating that corona. I can't say we've got all the answers again, but I think we've made quite a bit of progress. We know that the magnetic field is really important, and we know that the magnetic field channels energy from beneath the surface. Remember, the core of the sun is 15 million, so the core of the sun is much hotter. The magnetic field is channeling energy up, and what's happening is that the convection at the base on the surface of the sun is twisting those magnetic field lines up, and the magnetic energy is then, the magnetic field is getting twisted as it emerges, getting twisted, and it reconnects. Now it can reconnect, it can change its configuration from a very twisted one to a smoother one. It can do that as a flare, or it can do it on small scales all over the sun. And that green image I showed you of the sparkling diamonds all over the sun, it was happening on very small scales all over the sun. And even in the active regions, we think there are lots of strands that get twisted up, and the magnetic energy can be released in the atmosphere of the sun and heat the atmosphere of the sun. So it's being channeled up through the photosphere, the magnetic energy, and then it's being released up in the corona.
Professor, that was an excellent lecture. I just have two questions for you. The first one is, in astrophilosophical terms, is a solar flare an attempt, a nihilistic attempt at directed towards entropy? One. And number two, what do you think is the philosophy of the sun?
Woo! That's a big one. I'm not entirely sure how to answer that one. I guess the entropy is the chaos that's being provided by the solar flares. And we know that everything is in some ways getting more chaotic, so maybe they are contributing in that way. The philosophy of the sun, I think the sun has been fundamental to humankind since we first realized we were here. it's been worshipped as a god, and it's still held in great reverence, obviously, because it provides everything we have. It provides light, it provides heat. Without the sun, we're not here, and we're just at the right distance as well to profit from that. So I think that it's no surprise that many civilizations in the past have worshipped it. And as I expressed, what the thought of it actually not rising or going out is so horrific, actually, that it's even a little bit frightening to those of us when we see an eclipse that know what's happening. So it holds an important place, I think, in our lives.
And I think that's a very good place in which to stop. So thank you so much.